All right. So welcome to this Redox practice test. Let's go ahead and just jump right in. So which substance is a reducing agent in the given reaction? So to do this reaction, we're just going to go ahead and first eliminate the things that we add. This is acidic, we know, because we have H plus and H2O. Cool. So that leaves us with, and again, it's asking a reducing agent. So we're looking at the reactant side. Usually we're always looking at the reactant side. So we're looking at these things right here, MnO4 minus and SO2. So reducing agent is going to be the thing that oxidizes. When we say oxidizes, what we mean is the oxidation state increases. In other words, we are losing electrons. Because oxidation state is kind of like charge, and if we lose electrons, we get more positive. All right, so MnO4 minus. Each oxygen is 2 minus, and we have 4 of them, for a total of 8 minus. The overall charge is negative, which means Mn must be 7 plus to balance. From 7 plus, Mn goes to 2 plus. So Mn is having its oxidation state decrease. So this would be reduction. Therefore, if manganese is reducing, sulfur must be oxidizing and SO2 minus. So our answer here is D. Number 2, which of the following species would sulfur be reduced if converted to SeO? So if it's reduced, that means it's going to be decreasing oxidation state. So let's find out what it's going to end at. Each chlorine is 1 minus, but we have 2 of them. So this must be 2 plus to balance that out. So we have to decrease or reduce to 2 plus. So let's start with A. S2O3 2 minus. Again, each oxygen is 2 minus times 3 of them for a total of 6 minus. The overall thing has a 2 minus charge, which means sulfur is going to be 4 plus, but we have 2 of them, so each one's going to be 2 plus. If we check this out, 2 plus plus 2 plus, that's a lot of pluses, plus 6 minus, we get an overall of 2 minus, which is the overall charge. So nice. So sulfur is 2 plus. Now, 2 plus does not decrease to be 2 plus. In fact, those are the same. So there is no reduction. It doesn't actually change. H2S. Well, each hydrogen is 1 plus, and we have 2 of them. So this must be 2 minus. 2 minus increases to 2 plus. So it can't be that either. Sulfur is 0 on its own, which also increases 2 plus. Process of elimination, it's SO2. D again. We can just double check. If this is 2 minus times 2 of them, this must be 4 plus. And 4 plus does decrease or reduce to 2 plus. All right, how many possible electrons are needed when the following half equation is balanced using the lowest possible whole numbers? Well, I'm going to start off with nitrogen and nitrogen. Both have 1, so they're good. Next up is oxygen, 3. So I'm going to go ahead and add 2 oxygens to H2O. So I have a total of 3. Then I'm going to add 4 hydrogens to balance that out. When I look at this, the overall charge is 4 plus 1 minus. So that's going to be equaling 3 plus. Our product side has no charge. So we're going to add 3 electrons to balance it out. C. Which species could be reduced to form NO2? It's the same thing as the last one with sulfur, where we're going to look at what decreases to get nitrogen's oxidation state. Oxygen is 2 minus. We have 2 of them, so nitrogen must be 4 plus. So which of these will become 4 plus when they decrease? Well, N2 is 0. NO3. Each oxygen is 2 minus times 3 of them. That's a total of 6 minus. The overall thing has a charge of negative, therefore meaning nitrogen must be 5 plus, because 5 plus and 6 minus make a total of 1 minus. So there's our answer. It's already B. B starts at 5 plus, and then it reduces to form 4 plus. All right. Moving on to number 5. What is correct for the redox reaction? Well, we're looking at reduce and reducing agent. Another way of saying reducing agent is just the thing that oxidizes, like problem 1. So we can automatically eliminate B and D. The reason we can do that is because it's not going to be H plus. And that is an answer in B and D because we add those into our half reactions. So now we're just looking at which one's reduced, manganese oxide or iodine. I actually prefer to go to iodine to this one because iodine already has a charge here and has no charge here, and it's not bonded to anything. So in here, it's 1 minus. And here it's 0. That is an increase. That is oxidizing. Basically, it loses an electron. So therefore, wherever iodine is the oxidizing agent, or sorry, wherever iodine oxidizes, being the reducing agent, is the answer, A. All right. Which species does sulfur have the same oxidation state? Again, we're just looking at oxidation states. As SO3 2 minus. Well, if we look at this and we look at our oxygen, this is going to be 2 minus times 3, which is a total of 6 minus. Our overall charge is 2 minus, so sulfur must be 4 plus. S2O3 2 minus, we already know this is 2 plus. We did that one all the way back up in number 2. We already figured out that this one is 2 plus. Go back if you need to do it again. In SO4 2 minus, well, SO4 2 minus and SO3 2 minus are the same thing with the exception of an extra oxygen, meaning that this sulfur has to compensate for another 2 minus charge. So this is actually going to be 6 plus. I can just guess that, but we can do the math as well. 2 minus times 4 equals 8 minus. The overall charge is minus 2, meaning this is 6 plus. All right, H2S. H is 1 plus, therefore sulfur is 2 minus to compensate for the 2 H's, leaving us with our answer of D, which has to be correct. But we can work it out. Oxygen is 2 minus, each chlorine is 1 minus times 2 for a total of 4 minus if we add those together, meaning this must be 4 plus. That is the same as sulfur and SO3 2 minus. All right. The following occurs when metal X is added to Y sulfate solution and Z sulfate solution. X, Y, and Z represent metal elements, but not their symbols. What is the order of increasing reactivity? Well, we have to remember from our lab that if we take a piece of metal and we put it in a solution and it reacts, solution, we know that the metal is more reactive. Therefore, if it doesn't react, no reaction, the metal is less reactive. And that's just the inverse of the first statement. If metal reacts, it's more reactive. So when we see X and Y have a reaction, we know X is more reactive than Y. When we see X and Z have don't have a reaction, we know X is less reactive than Z. So it says increasing reactivity. So if we put the most and the least, you know, X is in the middle, Y is less reactive, Z is more reactive, and that gives us B. All right, time for some real equations. Both acidic or basic solutions respond to the questions based on this. Now, here's the deal. I am going to give you the full answer for the basic one, even though it does not exist, because once again, this is vinegar and acid, but we can still solve it. And so I'm still going to solve it just to demonstrate it. So for this reaction, we're going to start off with what is reduced. and what is oxidized? We can kind of answer both of those at the same time. I'm going to start with this first thing, Cr2O7 2 minus, and I'm going to determine the oxidation state of chromium. So oxygen is 2 minus, like always, times 7 equals 14. We have an overall charge of 2 minus, which means we only have to account for 12 of the minuses, meaning that each CR, because there's 2 of them, it's going to be half of that. So each CR is 6 plus oxidation state. It ends up at 3 plus oxidation state. That is our reduction. So you have 3 answers. You can say Cr, chromium, or my personal favorite, just write the compound, Cr2O7 2 minus. Therefore, what is oxidized? That will be the other thing, C2H5OH. Or specifically in this sense, it's C or carbon. But again, I'm going to prefer the actual compound. What is the balanced reduction half reaction in an acidic solution? Well, we'll start with Cr2O7 2 minus. It becomes Cr3 plus. I need to double that, and I need to add 7H2O. So to balance the 7 hydrogen or 7 H2Os, we have to add now 14 hydrogen ions to the right. This is acidic, so we can only add H plus and H2O to either side. Finally, we have to balance the charge here. So we're going to go ahead and I'm going to indicate our charge under it. We have 14 positive, 2 negative versus our 3 positive over here. We have a total of 12 positive on the right side. And sorry, my mistake. It's not 3 positive. It is 2 times 3 positive to account for our coefficient for a total of 6 positive. So to balance it out, we're going to add 6 electrons to the reactants, and then we have a total charge of 6 positive on both sides. That is our balanced reduction half reaction. Moving on to the oxidation half reaction, we're going to start with vinegar, C2H5OH. We are going to then oxidize that to CO2. Once again, we have to first start by doubling the amount of carbon so we can match it. Then we'll identify that we have 4 oxygens on the right side, 2 times 2. Well, we only have 1 oxygen on the left side. So we're going to go ahead and add 3H2O. When we take in our 3H2O, so 1, 2, and then we have 3 of those, so that's 4. We end up with now 3 times 2, 6 hydrogens, plus another 5, that's 11, plus 1, 12 hydrogens. To balance it out, we'll add 12 hydrogens to the right side. Again, these are hydrogen ions. So now when we look at the charge, we have a net 0 on the left and a 12 positive on the right. To balance charge, we'll go ahead and add 12 electrons to the product side. And charge is balanced. Those are 2 half reactions. We can now combine the whole thing by just multiplying the reduction half reaction by a factor of 2. Our electron values cancel out, and then we will go ahead and write the completed reaction, and then we will combine like terms at the end. So we have 28 hydrogen ions plus 2 dichromate, Cr2O7 2 minus, plus 3 water, plus 1 vinegar, C2H5OH. That will turn into 4 chromium ions, 3 plus another 14 water, plus 2 CO2, plus 12 hydrogen ions. Like I said, we're going to finally combine like terms. So 12 hydrogens on the right combined with 28 on the left, and we end up with 16 hydrogen ions on the left. The 3 waters on the left combined with the 14 on the right, and we end up with 11 waters. And I'm not going to rewrite the whole thing to save time. You don't have to either. All right. All right, so we're going to do this in basic solutions, even though I would not provide it for an acidic solution like one with vinegar, but we can do it anyway, so we're going to do it anyways. We're going to start off with our balanced reduction half reaction. So once again, we have dichromate, Cr2O7 2 minus. That reacts to form Cr3 plus. I'm going to balance out the chromium by adding 2 to the right side. And then now I can add either hydroxide or water. So I'm always going to add twice the amount of hydroxide as I need. So that's 14OH minus, and then half that much water on the other side, 7H2O. All right. Now that I have balanced that out, I have to add the electrons, which, if we remember from before, it's going to be honestly quite similar. So we have 2 minus here, and we have 6 plus 14 minus for a total of 8 minus. So to balance that, I'm going to add 6 electrons to the left side, which should be predicted. So as before, we've added the same amount of electrons on the left side, which should make sense according to redox theory. So moving on to the balanced oxidation half reaction. Again, we're going to start with C2H5OH. That's going to turn into CO2. So I'm going to start by adding 2 carbon to the right side, or 2 to the CO2 to balance the carbon. What I want to actually do here is focus on balancing the hydrogens first, because I know my rule for balancing oxygens using hydroxide and water. So I'm going to start by balancing the hydrogens. I'm going to add 3H2O. So now that my hydrogens are balanced, I'm going to move on to balancing the oxygens using the rule I understand. So I have 7 oxygens on the left with 1 oxygen on the, 7 oxygens on the right, 1 oxygen on the left. So I'm going to add 6 oxygens. So I'm going to add twice that many first. So I'm going to add 12 hydroxides and then half that many waters, 6 H2O. I can then combine these, and I will erase it over here and make a total of 9 H2O. Now to balance out the electrons, I have 12 minus here, so I'm going to add 12 electrons to the right side, and I have the exact same electrons on both sides. So to finally balance this whole thing out, we're going to do exactly the same thing. We're going to multiply the top by 2. So the last step, after we've multiplied both sides by 2, we get to add our final reactions together. I'm going to cancel the electrons on both sides because those will cancel out. And I'm going to add 14H2O plus 2Cr2O7 2 minus plus 12 hydroxide minus plus C2H5OH, and that is our reactants. Our products will be 4 chromium ions, 3 plus 28 hydroxide ions plus 2 carbon dioxide plus 9 H2O. The last thing you can do is cancel the same things on both sides. So our 9 H2O will cancel and leave only 5 water on the left. The 12 hydroxides will cancel and leave only 16 hydroxides on the right, and you're done. So there's one more problem on this test, but I want you to really try and use what you have learned here and work that one out on your own. I will still post the answer key for that problem online, but you can solve it yourself. Good luck.